Are you in this?
No.
When are you in this?
I got the email, but I don't want to pay dues. So
I don't either.
I've decided that all honor societies are bogus, and I'm not paying money to be a part of any of them because I don't care.
No, but I want to put on my best book.
Good on my resume though. Majored in physics, minored in math. I was in society for both of those things. So how you guys doing?
Good.
How do you request an unofficial transcript?
You go to the internet and look at your transcript, and then you click it.
What, how do you do that?
Right, click.
No, how do you see your transcript?
I don't think I have a transcript
Student
anymore, but
records.
I can look at the banner web.
Academic transcript. Submit it.
Bro, has this always been here?
Yes, unless you have a hole in your.
Whoa. Well, that is freaking awesome. I didn't know that was there. I thought you had to request it.
Not for unofficial.
For the official one, it's they're not there.
Also, what scam do you have to pay for your transcript? Like, those are my grades.
Seriously.
Agreed.
A lot of education is really just a scam, and I hate it. It needs to be better.
That is quite true.
Some good news though. Well, assessment day might not be good, but a good announcement about it. Don't have any class or lab that day, just to avoid any complications for anybody. I don't have anything going on that day, but I'm going to assume some people do, so I'm just going to call no class that day. And since there's no lab that day, there just won't be a lab next week. This plays well with my schedule because if I'm not having class next week, then since we're kind of starting chapter 16 a little bit late this week, since we spent Tuesday doing mostly homework, people won't really be ready for the next lab yet anyway. It'll be about resistor circuits, and I know that the resistors work, so that should go smoothly. So, summary. No class on the 16th at all. So just take the day to yourselves, do whatever it is you have to do that particular day, or sleep if you have nothing to do that day. And there won't be any lab that week at all. The week after that, we will have a normal lab, is the current plan. Currently, chapter 15 homework is due tonight. It'll open up with a chance for you guys to ask any other questions you have about it. What it says on WebAssign right now is that chapter 16 is due next Thursday. I kind of knew we were starting it late, so I didn't make it next Tuesday. That's currently due next Thursday, but I'm planning on changing that to the Tuesday after, so that this particular section has 2 full meetings, this one and this one, before that assignment is due. So that kind of to get back to normal, considering all of the jumps and such. And I've tried to summarize all of these things here. No class next Tuesday, no lab next week. Homework, 15 homework due tonight, 16 homework is due here. Any questions, comments, concerns about any of these?
I think I know what my idea is.
Okay, hope that goes well.
Guess you can't culture for having a breakthrough.
I mean, if I don't act on something the moment it pops into my head, I will forget within the next 30 seconds, and it just won't get done. Which is why I end up sending a lot of weird emails at 3 a.m. Because if I don't, it's not going to send. Okay. How's the chapter 15 stuff going?
last class was really helpful.
I am glad. I'd rather spend time in class than you guys being frustrated or confused all week.
Don't worry, have other classes for the frustrated piece part.
Oh no.
Shout out Linear.
I am some type of mathematician, and I find most pure math classes frustrating and confusing.
It's like the proofs and definitions and the theorems, that stuff is fine, but when I actually have to do the calculations, it's like, what do they call it? The name of my existence area,
Oof. Your antithesis is math.
which is, probably not conducive to me being a math major, but
Oof. Excuse me.
Hey, there you go.
Amen.
Any specific questions from you guys about the 15 assignments? And if you have one later in the class, do please ask about it, but any that you guys have at the moment.
So the first two, I've gotten them wrong 4 times.
Oops.
I'm okay with like not getting 100 on it. If I send you my work, is like, I don't know why I'm getting them wrong, but like I'm pretty sure I'm doing them right.
I know one of them, there's a little bit of weirdness that has occurred to people due to the way it is asking for the angle. Let me check real quick. Because since some of these assignments are old ones that I have made in the past before I have rechanged how the grading system worked. Okay, this assignment will allow you to submit more than 5 attempts.
Cool.
So if you're on 4 attempts, please do keep entering things. I've seen some issues with number 1 about the angle, the way that it wants the angle written here.
That's the part I got wrong.
Okay. So the way that I draw this particular problem, we care about all the forces acting on this particular particle. So we have one force from this proton that's going to push that way, one force from this, I call them protons, they're different charges. One force from this positive that's going to point that way, one force from this negative that's going to point this way. So ultimately, our net force should point somewhere into the 3rd quadrant. And the way that WebAssign is looking for the answer, and because WebAssign is asking it in a atypical way, I can, if you send me your work and the work is correct, I can show you how to put it into the WebAssign exactly. Counterclockwise from the positive x-axis. So it wants to know that angle.
So would it be 90 plus whatever the angle is for the hypotenuse if you were to make a triangle with those 3 points?
Isn't that clockwise though? It wants to go like up.
It wants them to be.
Oh, you're right. Sorry.
Oh.
There's 2 answers. Like, if this version of the question, WebAssign first is looking for negative 103. Sorry. It says counterclockwise for positive x is positive, which is why this is negative 103. I think WebAssign is defaulting to that one because it's the smaller of the 2 numbers.
Right.
And if it's
But
negative,
if you go the other way and it's a positive number, it's just bigger, it also.
it will also count as
Okay.
correct. So with this set of numbers, WebAssign should accept 103, and additionally, it should accept 257.
I think the numbers haven't changed. I don't think the numbers are different.
Now, the 2 vectors being added together. positive, force from the positive, force from the negative. Solve for hypotenuse. I draw it like this, such that theta appears in that particular spot. As long as you know this theta, the two ways to get to the final answer from, if you've drawn it like this, and this is theta, you could either do 180 plus that theta, which would represent from here counterclockwise around. You could also do theta minus 180 to get the other direction.
Okay.
And I know that on the drawing, the blue vector would normally be down here, but I like putting my vectors tip to tail so that the hypotenuse appears where it normally would, and so that theta appears in the healthy position. That's just how I draw them. Do you think that will help, Nancy?
I think so. I was using, well, I was using the wrong angle. I like got the correct magnitude, but then assigned that magnitude to the wrong line.
Oops.
Happens to the best of us.
Yes, it does.
So if I like fix it, I think I'll be okay.
Okay. You also said 2.
2 is not, it like should not be hard, and I cannot, like I can't tell you why I keep getting it wrong, because I'm following the one we did in class.
This is very similar to the one we did in class. The main difference is that the two strings connect in the same point. So the distance between them will just be the legs of these two triangles. There's no extra piece there.
Right.
It should work the same way. We know the mass, therefore we know the force of gravity on each. We know string length. We know the theta, so we can figure out the other parts of the triangle. What is the magnitude of the charge hemisphere? Yes. Our work for the sample question with the two hanging strings should go the same way. If you want to, if you keep having issues with it, you can show me your work and I'll better see what happened there.
I'll just send you my work. I'm really not too torn up about it.
Anything else on your mind about it, Colin? Okay. They're due tonight, so be working on them and send me any questions you have as soon as you have them. Because if you send it at 11 p.m., I'm going to be falling asleep. And timing might not work out there. So, sooner the better. I'll keep this tab open in case you have any questions during the lecture. And today, we'll be beginning the capacitance notes. The lab this week is about capacitors. I have tried to address briefly what capacitors are when examples related to them show up in our notes and our examples. So this information shouldn't be entirely unfamiliar, but we're going to start doing more math about it now. So we're entering the realm of circuits and individual parts of circuits. And the word capacitor as an object refers primarily to a specific circuit component. So if you've had classes where you've built circuits out of batteries, wires, light bulbs, etc., you've built circuits, and if you haven't done that, then you've probably seen a circuit board in a movie or in a sci-fi thing somewhere. And all circuits, a circuit at its most basic, I'm going to use conventional symbols. You have some power source like a battery connected via wires to some thing. Let's use a light bulb. And it has to connect back to that source. There should be one continuous path for the electrons to flow through from beginning through the thing that you're powering and back to the other end of the source. All circuits, no matter how complex, are still follow this rule at the most basic. You just add more and more things in, more connections, more components, etc. And capacitors are one of the things you can insert into a circuit like this that accomplishes a specific task. As for what a capacitor physically is, we talked about it briefly. If you have, say for example, you have a plate like this, a solid plate that is positively charged, what's the E field coming off of this plate going to look like?
Goes out.
Out in all directions, yes. But, and I might not have said this out loud yet, E fields are emitted perpendicularly to the surface creating them. If we were looking at a proton, which we generally consider to be round, that field's going to come out radially in all directions. But this plate, we are drawing intentionally kind of square and boxy-like. So the field lines, at least for each side, are going to all point straight out in the same direction. You don't get this with single charges. You can only get this with larger objects that have a net charge. And this is neat because since all the field lines are pointing in one direction, we know exactly what direction something is going to move in when you put it in the field. It will either follow the lines if it's positive or follow them backwards if it's negative, which is handy. We use these sorts of things as literal ion accelerators for vacuum tubes in our TVs or the Rutherford gold foil experiments. You want a nice uniform single directional field so that you know you are sending particles in X direction. Now, I'd say the weakness of just one plate is that the field is going to get weaker the further away you get. If we were to draw like y-axis lines, every point on this line would have the same field strength, but every point on this line would have a different but weaker common field strength. So it still gets weaker the further out you get, it's just the same at each distance from the plate. Subsequently, if it was negative instead, the field would behave similarly, except it would point into the plate. But it would be uniform at each distance, but it would get weaker the farther away that you get. But you would still have the same net effect. The field is all pointing in the same direction. You know exactly what direction a particle placed in the field should go. And so some very smart people put their heads together and realized, what if we just put a positive plate next to a negative plate? And uniquely, the E field in this object, this pair of objects, is uniform all the way through. All of the E fields we've been looking at so far always get weaker the further away from the source you get. But in here, if you get further away from one source, you're just getting closer to the other one. And if you build it right, that means the E field inside is the same at any point inside of the object, which is really, really, really nice for all of those purposes we mentioned before, because physics works best when numbers aren't changing. As soon as numbers begin changing, all of our formulas have to change, and everything gets exponentially harder. So a good constant E field is wonderful. And this, at its most basic, is what physically makes up the component, the device, called a capacitor. If you ever, Radio Shack is dead, right? That doesn't exist anymore.
Yeah, it doesn't
There's
exist.
still one in Somerville.
But, okay.
Some
Privately owned, but it is a Radio Shack.
Well, potentially that particular Radio Shack might still sell regular electrical components to people. You can still get them online, you just have to go to like, I don't know, Hobbyists R Us, basically. The capacitors I have on the lab tables in the other room, or if you could get them off the shelf at an electronics store, would look something like this. This is what you would actually jam into a circuit. One end plugs in here, the other end plugs in here. It's like a can with little tin legs. And what's inside of this is 2 parallel plates, one of which is connected to one of those 2 legs, the other of which is connected to the other. Notice the 2 plates aren't touching, because if they are, you don't have a capacitor anymore. You just have the 2 plates that are separated. One will become positive, one will become negative. There's some amount of space between them. There might even be some specific kind of material, like sandwiched between them. Usually some type of styrofoam or aero type material, usually to make sure the plates don't touch. But really any material will do, even air, technically speaking, as long as you keep the plates from touching. And once the designers have this point where they've got the 2 plates and they are separated, they literally just roll it up like those tube sandwiches that they slice and serve as little circular helixes, and just put it inside of that plastic housing.
So it's the spiral inside.
Yep, they literally just and as long as they make it right, as long as they make sure no plate is touching any other plate, and as long as they make sure one plate doesn't fold over and touch itself, it should capacitate as normal, even though it's not a can. So the parts that make up the physical capacitor are the 2 plates and whatever material you put between them. That material does have a name, a dielectric, because this is worth categorizing, because sometimes it's foam, sometimes it's air, sometimes it's rubber. So this does play a factor in how the device turns out. The function of this particular apparatus is that it stores electrons and electrical energy inside of its E field. When one of these is wired up, electrons will enter the circuit, actually onto the negative plate. They'll all be hanging out on the negative, and they don't want to be anywhere near each other, so they'll slowly begin traveling through the field to get to the positive plate. Subsequently, if you had positive charges on this side, they would slowly make their way over to the other side. Doing this literally stores up a bank of charges inside of the field, because they're in there until they're done transferring from one side to the other. So a capacitor has a certain capacitance for holding charges within itself. But as it's holding charges, it's also holding energy, because those charges, as they are moving through a field, have and are transferring and are changing energy types. So since it holds charges and holds energy, these can act as batteries. If you charge up a capacitor and then allow it to discharge what it has charged up, it will let its energy out and power something until it runs out of energy itself. So these did form some of the earliest rechargeable batteries. Additionally, these were also the first touch screens. I assume most of your smartphones today use the type of screen where only, like, if human skin touches it, does it register something? Meanwhile, old, like, Gen 1 Blackberries, where you could poke it with the end of a pencil and it would register. Does that sound familiar? Nintendo DSs and 3DSs were the same way. Anything could touch it and it would work. but it had a very different kind of texture to it, and you could literally like feel like pressing into the screen to make it work. Those types of touch screens were themselves capacitors, and when you touched part of the screen, you literally formed a dent on one of the plates, which changed the capacitance of the circuit. Because the distance between the plates is one of the things that affects the capacitance of the capacitor. So when you press into it, it changes, and it's based on, the system can analyze where it changed to figure out what you're touching, and then tell the computer to click here.
So then when like a DS or something died, and you like plugged it in, it just recharged this whole thing?
And every other part of the system that ran on electricity, but yes.
So what's the difference between a capacitor and like a conventional battery?
Conventional batteries rely on chemical reactions to do their jobs. And I will fully admit, I myself am not entirely sure how a chemical battery is recharged. I know that one-time use, non-rechargeable chemical batteries have chemical reactants in them, usually lead or lithium based, that the reaction commences, and as a byproduct of that reaction, it just gives off a whole lot of electrons. And they come out of one end of the battery, close the circuit, and come back.
Would a capacitor last longer than a battery?
It entirely depends on the capacitor, the battery, and what you've got them hooked up to. The problem with a capacitor is that it needs to be energized first, whereas if you just pour the battery reactants into each other, you just get the reaction.
So why did like old batteries like explode and get like battery acid and stuff?
Well, I know that like a AA battery will begin leaking its lead and or lithium components into the water over time. I know that, actually, I end up changing these like once every 3 years. And sometimes if there's any water that drips in, when I open this thing back up, there's white dust everywhere. That is corrosion from the chemicals inside the battery leaking out and reacting with water.
That doesn't sound dangerous at all.
It is dangerous, but once it's reacted, it's at least not explosive. That said, don't lick it.
Not every children's toy that has batteries in it though.
You're telling me not with batteries, that's how we did them work back there.
Please don't lick
Wait,
batteries.
Never mind.
There was no explanation for it, but you look into that thing, you put it back in there, and start working. It makes sense.
I've never heard
I've never
this.
done that.
I've definitely done that.
I've heard
I
of
take
licking.
them out and switch them, or I'll like shake them and put them back.
I have also done that.
We used to put it in
I
the
have
freezer.
swapped them. This thing died recently. I reversed 2 of the batteries and it worked again.
That makes no sense.
I don't have a good reason for it either.
It's fake.
Electricity's fake. It's all an illusion. Live in the matrix.
It's like when you would blow into the N64
But is
part.
the-
No, that made it worse.
No, it made it work.
Okay, that got dust out, but you also blew in saliva, which would corrode the pins of the cartridge.
Okay, that may be true, but why did it work? What I'm thinking.
Okay, it worked in the moment because it got the dust out. Long term, it would break the cartridge. You want to use a can of compressed air.
The cartridge is
Because I had
bad.
that as like a 3-year-old.
None of us knew what we were doing. No one read the manual. I completely lost my train of thought there. So, that is what a capacitor is. Physically, they exist in circuits to hold electrical charge and to hold electrical energy. Sometimes this is done to keep those charges and energy away from one part of the circuit, or to funnel it to a different part of the circuit, or to hold on to it for later, or to make a touchscreen work, or vacuum tubes or any other things we talked about.
Basically, it did all.
They're very handy. I think the only single thing that is more useful is a transistor.
We don't want to know those in this house,
Not especially. That said, they're very important because they're the reasons our machines keep getting smaller. You know how a radio used to be the size of a person? Transistors are the reason it now fits in one microchip. Yep. Do you have a question? Sorry.
Potato clocks, are those more like the chemical battery?
Yes.
Okay.
I think the chemicals inside the potato react with the metal probes you jam into the potato.
Okay.
And that reaction causes electrons to start jumping around and flowing.
Okay.
I haven't actually built a potato clock.
I've done.
I think I had a potato radio set that I never finished because I have the attention span of a rodent. Yes.
That was just a me too.
Run it to crazy, they'll eat your game.
So
Mm-hmm.
do all of like the positive charges and the positive plate have to be the same? Or is it just like generally, like this is the positive side?
If you take one object and you charge it, the charge tends to become uniform across the entire object.
Okay.
Let's say, for
If you
example,
do
this
that
was
with
just...
magnets, or is it uniform?
Magnets are technically very different to everything we've been talking about.
Okay, never mind. I didn't say that.
I do have a lot of magnet related.
There are some fundamental similarities, but magnetism and electricity are technically different but related phenomena.
Okay.
You're not wrong to compare them. You are correct to compare them. Just none of the math we've done works on those. If this was a hunk of metal and I just threw a bunch of extra electrons into it, those electrons would evenly distribute themselves throughout the metal because they don't want to be near each other. They just try to get as far out as possible, and that tends to create a uniform distribution where the charge across the entire thing is the same. And same thing happens here. You can force one object to have different charge levels on different sides of itself, but that tends to be forced. Excuse me. It's called induction, I think. So, let's say, hypothetically, we have our capacitor. It has the nice uniform electric field inside of it. We know which plate is positive, we know which plate is negative, and we are going to drop a proton right here. Conceptually, off the top of your head, what's it going to do next? If it's just allowed to do whatever it's going to do. Going to zoom over that way. Very good. Not a trick question. This is incredibly similar to this.
Yeah.
It goes one direction.
It goes in one direction because there's a field, and this particular object has potential inside of that field. For gravity and masses, any object with mass inside of a gravitational field has different levels of gravitational potential depending on where it is in that field, which just boils down to how high above the ground is it. The higher something is, the more potential it has, which means it's going to have more energy more kinetic energy when that potential is released. It's the same thing here, just swap every time I said the word gravity with the word electrical. When this proton is next to this positive plate, it has very high potential because it doesn't really want to be there. It has a lot of energy stored in it that it's going to use to get away from this thing. Yes?
So is there ever a point where the positive one is going to not be positive anymore? Where like all those electrons are going to want to go over to, or go around? Okay. Well, I guess never mind.
If you turn the capacitor off and disconnect it and let it discharge, I think both plates would eventually become neutral again. But as long as it's plugged into a circuit, one side will be more positive than the other. And often that's usually all you need.
The space between the two plates, does it work like better or faster if they're as close as they can be without touching?
If they're as close as they can be without touching, then that does increase the capacitor's capacitance because it makes it easier for things to get from one side to the other. But it does mean there's less space for that proton to accelerate in. So if I drop this marker from here, not a whole lot's going to happen. If I drop it from here, I get a little bit more oomph once it reaches the other side.
So it's more about the charges than the distance.
The distance plays into it. The E field also plays into it. The thing about Earth and gravity is we assume that the gravitational field is constant and pointing straight down across the entire surface. It gets a little weaker the higher you go, but not enough to matter. So across Earth's surface, it's just assumed that the field is the same, and all that's really changing is how high up you are. Capacitors can have all different thicknesses and all different field strengths within them, depending on lots of other properties. If hypothetically you had two capacitors with the same E field, but one was thin and one was thick, but the same E field in both, then a proton would be able to accelerate up to a higher speed before striking the other side. So a bigger one with the same E field in it would store more energy.
It's bigger this one.
Yes, if the plates were further apart, but it still had the same E field. That'd be very hard to build.
Wait, explain it.
So this is a tiny capacitor with a tiny width.
It's just one of these things.
This is a big capacitor with a big width. They're both happy. If somehow the E fields in both were the same, if these capacitors had the same E field, the only main difference is just how thick they are, then one particle accelerating from one side to the other here would not have as much time or space to accelerate as this one.
So what, are you saying they would hit the other side at the same time?
They would not.
What are you saying? Like, what's like the,
It's like comparing this to this. Ow.
Why is it so hard to get the E fields to be the same?
Because when you're building a capacitor, the three main things that affect what its capacitance is are the surface area of the plates. Usually the bigger the plates, the more capacity it has. How far apart they are. The further apart they are, the weaker the E field is going to be because they're further apart, which means you're going to have to crank some other variable really high upwards to compensate. It also matters what you sandwich between them. You usually want something between them to keep them from touching, because if they touch, then you don't have a capacitor anymore, you've just got a circuit with extra steps. Like if I just put a wire between here and here, the charges wouldn't accumulate, the current would just flow from one side to the other, you wouldn't get the E field.
Then what's the advantage of having a capacitor if it's not using?
The advantage is it can store charge within itself, whereas a wire it passes through. It doesn't linger. Sometimes, depending on your design, you need or want a certain bank of that energy built up so that it can be directed or used somewhere else. Sometimes you can also use it as a gateway to stop electrons from going somewhere else because they get stuck in the capacitor. a ton of electrician reasons to use them, but a lot of them do get hyper-specific.
So that little cube on the board,
Mhm.
it'll zoom over to the negative side, and in doing that, will pick up energy. Or
Well,
will expel energy, which one is it?
its potential energy will become kinetic energy.
So it has
Same as
potential
this.
energy sitting on that side, just like the marker has potential energy when you hold it up.
Mhm.
But when you drop it, that turns into kinetic energy.
Correct.
And when it goes across, that's kinetic energy.
Right. If you dropped a proton right here, it would accelerate to the other side. Its potential over here would become kinetic over here. So, like how there is gravitational potential energy, there is also electrical potential energy. And all charged objects have some amount of potential when they are in a field. Again, all of our electrical diagrams and terms are from a proton's perspective. So, as far as a proton is concerned, it would have high potential next to the positive plate. It doesn't want to be there. It has a lot of pent-up energy it's going to use to move. Meanwhile, if it's next to the negative plate, it's going to have low potential because it is where it wants to be. It doesn't really want to go anywhere else. So traveling from one side to the other takes its potential and turns it into something else. And out of all of this stuff on the other side, this is the main formula for your notes. The change in potential energy as it crosses from one side to the other depends on its charge, the strength of the E field, and how far it goes.
I'm confused on how the E field is a number. I thought it was like a thing.
It is a thing, and the number tells us how strong it is.
Yeah,
Okay,
so
can you
we-
explain the difference in charge, E field, and voltage?
I can. Charge is an innate property of matter. Like how all subatomic particles have mass, they also have charge. It's an innate feature of those particles. Physicists often have a hard time explaining exactly what matter is and why it exists. We have an equally hard time explaining why those same things also have charge. It's just a property of the thing that exists, and you have to go back to the very beginning to try to figure out why. Objects that possess charge, be they the particles, the fundamental particles themselves, or whole objects with an imbalance of those particles, if something has a net charge, it gives off electric field. That's its way of sort of exerting its influence on the universe. Every single charge gives off a field. Subsequently, every charge reacts to other electric fields. So, objects have charge. Objects with charge make electric fields. When something with charge is in an electric field, a force is exerted on it by the field. And you can take all of that, replace charge with mass and electricity with gravity, and you have the same thing for when things fall. So, in this specific situation, there's a charged particle inside of an E field being made by other charged particles. This particle is going to act because in that field that it's currently inside of, that field is going to exert a force on it, and forces have a tendency to do work. So as that force pushes the particle a certain distance through the capacitor, its potential energy is going to change and become kinetic energy as it moves to the other side. It turns out you can never escape potential and kinetic energy. Just like you can't escape triangles or Newton's second law.
Not yet.
I'm sure quantum mechanics has some way to factor that in,
What? Triangles?
probably.
I
Maybe
don't-
not.
I don't
I had
know.
never actually studied quantum super in depth. It scared Einstein, so it scares me.
Well, we haven't studied it at all.
So which one of the cubes you drew on the board would be better? One that has more, you could get more kinetic energy from? The bigger one would be better?
Oh. Yes. If you have these two objects and they both have the same E field in them, this one could hold more energy.
But since that one's farther apart, then it's most likely not to be able to have the same E field, right?
Right, it would have to be very specifically made to accomplish that.
So what if it was just had its normal E field that it would have? Which one would be better then?
Probably 6 to 1, half dozen the other. I'd say distance apart is very important because in the E field formulas we were looking at, the radius term is squared. So the farther things are from each other, the weaker it's just naturally going to be. So I'd probably end up favoring the tiny one if the E fields weren't what was being held constant. I would say it would take you need a really powerful circuit for this thing to work.
So
If you
the
could-
charge would have to be higher on the big one?
Sorry, one more time.
For like the big one, their charge would have to be higher?
Yes. You would need a bigger battery to make the big one work at the same E field strength.
Okay, so if you had them both like this, can I draw a picture to answer that question?
Yes.
So if you had the little one, you had a big one, and you put a thing here, if you had like a marker that said like when it passed this point, would they hit like that point at the same time? But this one would just keep going, like when this was here, would this one be there?
If it was the same charge of particle, if it was a proton in both, and if they had the same E field.
And it's not going to just continue, so.
Correct. Just based on this formula, as long as it's the same charge of particle and the same E field strength in the capacitor, they will have the same energy change by traveling the same distance. The hard part is just making a really big capacitor with the same E field.
That's what.
Okay. You guys have this part in your notes? Okay. So, we're going to look at a hypothetical capacitor built to these specifications. The distance between the plates does tend to be very small because the farther apart they are, the weaker all the fields get. So they do tend to be very thin, generally speaking. This particular capacitor has its two plates, spaced 0.01 millimeter apart. This marker is dying. And the E field between these plates is 25 newtons per coulomb. We are going to drop one proton right in the middle. We are putting it here. It wasn't at the other end and accelerated at this point, we're just dropping it right there. If it is in the middle of the plates, oh no, last time. The very first thing we are asked, when we put it there, what is its final kinetic energy going to be? My first question is, in this situation, what is this proton going to do logically? All right, it's going to zoom to the blue side. And so we want to know its final kinetic energy right as it reaches the blue plate. Yes?
E field is a vector.
Sorry?
E field is a vector, yes.
It is a vector. So every E field line is pointing in the same direction, and they all have this strength thanks to this capacitor. So yes, E field is a vector. I should be putting the vector over it. So when we drop that particle in there, it now has a certain amount of potential because of where it is. That potential is going to drop as it moves toward the negative plate, and as it drops, that energy will instead become kinetic. So, as before, this is kind of a generalization. If potential energy is dropping, kinetic energy is probably rising, and vice versa. I do this negative in here because if PE drops, KE will rise by the same amount, and vice versa. So the negative is to make both sides have the same sign. So to find how much kinetic energy it has at the end, we need to know how much its potential changes from where we drop it to where it ends up. And the other slide, the one that I told you to write down on the other slide, is specifically for change in potential energy as you move through a capacitor. So this will tell us the change in potential energy. That'll tell us how much the PE dropped. It'll tell us how much the KE rises as it does so. Any issue with that? Okay. So for this specific situation, delta E negative, so Q, we want charge of a proton. E is the E field, and then delta X is how far it's going to go. What is the distance this proton is going to travel? Very good. We dropped it in the middle of these two plates, so it's only going to go half of the width it's going to go.
Do you have it in meters?
You do. So,
Why don't they just make the unit so that you can use the thing that you're probably going to use?
How hard is it for that?
That's what I'm
because
saying,
physicists, for some reason, decide on a unit or a metric and then run with it.
Because
no
like
matter how
all
much
of these
sense
are
it
like
makes.
just a negative whatever. If they would have just picked a really small unit,
Well,
then it would have been so much better.
correct. But I think they base a lot of the metrics on like human scale. So humans themselves are usually somewhere between 1 and 2 meters tall, as opposed to being between 1,000 and 2,000 millimeters
I
tall.
mean, you can use it different. Like I would, you don't have to measure people in meters. I feel like it makes sense.
You're right. I know for certain the reason we use kilograms instead of grams is to keep all of our forces from being 1,000 times bigger. Because that just scares people. Well, if we use kilograms to determine newtons, then I, sort of average human male adult, weighs about 1,000 newtons. If we use grams instead, and if we just defined all of our systems on grams instead of kilograms, I would weigh 1 million newtons.
Makes
Which-
you sound a lot bigger than you actually are.
Yeah, so my working theory is we did that so that we just wouldn't scare ourselves.
This number is supposed to be very small.
Yes. This number is supposed to be very small because you've got a very small number times an average size number times a very small number.
So,
I would bet my math.
So you guys have
Is it? Question.
answer.
There are 1,000 millimeters in 1 meter.
Correct.
So 0.01 millimeters divided by 1,000.
1, 2, 3.
That's it, divided by 2.
Oh, you know what? I did do that wrong.
Because I got 1 power up, or
Yes.
1 power less than you did. So I was trying to figure out why. It's 23.
It is? Would it not be 0.005 times 10 to the negative third?
Well, dividing this in half would make it 0.000005. You are, the point you made a second ago is ultimately correct, though. This
If
is
you
not a
write it in
whole lot.
scientific notation, then I'm
Sorry, say again. Oh,
like, because half of 0.01 is 0.005, and then times 10 to the negative third would be 0.000005, so with an extra zero.
I got 5 times 10 to the negative 6 as
Yes.
my like distance.
yes, that is
That's
correct.
what you got here. I don't really know what you're.
okay, yeah, that's the same thing.
Yes,
Yeah.
okay, but for some reason I'm getting the number you have, but I'm putting those. So let me do it again.
Did you cut it in half again, or?
I don't think
Times?
16 times 10 to the negative 19.
Wait, 16 times 10?
Oh, 1.6, that's why. There we go.
It happens. Okay.
My
so-
little number was right, it was a different one.
So delta PE is a small negative number, which means it lost some tiny amount of potential energy. Subsequently, based on this principle, it must have gained the same tiny amount of positive kinetic energy. And that is the answer to the first thing you've been asked. You are right that that is not a lot of energy.
So because it starts with no kinetic energy, so you just put it there.
Yes. Since we
The
dropped it in.
change is the final.
Correct. Since kinetic initial is 0, since delta KE should be final minus initial, if initial KE is 0, final KE will be this number. Yes.
Is like potential energy to kinetic energy, is that always exact? Like is the exact same
long as there's no other sources of energy at play, like if there was, in previous examples where there was a spring involved, when we were talking about larger objects, that would be one of the places energy would go, or friction. But if there's no other places, you can't assume one would be better. And for simplicity's sake, we're saying just one would be better. So, and since we just kind of took our cosmic tweezers and just dropped the proton right there and had no kinetic energy to start with.
So for speed, are you assuming that speed and velocity are equivalent?
I said speed because I never specified direction, but yeah, solid group, the magnitude of velocity. And let me go ahead and rewrite this as KEF. And KE is still 1/2 mv squared. So there's our KE, mass of a proton, find velocity.
What's the mass of a proton?
I think it's 1.67 times 10 to the negative 27th kilograms.
27, negative 27.
Correct. So I'm getting about 155 meters per second.
What is the mass of it? Gosh. Hold on. 1.67 times 27.
Wait, is it 10 to the 27th or negative 27th?
Times 10 to the negative 27.
What did you say you got from?
155. So pretty fast, actually. Electricity can bug it when it wants to.
Sorry, can you see that now?
1.67 times 10 to the negative 27th kilograms.
Is that a number we can memorize?
No. I only remember it at this moment because I've been saying it so much recently.
You got 155-ish?
Yes.
Why when you like, when you turn on the lights in like a big gym or something, it takes so long to come on? Why is that?
So I say that one more time.
When you're in like a big gym or something, you turn the lights on and it takes forever. Why?
It's probably because all those lights are on one circuit. And even though single electrons can move very fast, if we are ignoring like resistances of what they are traveling through, like a single electron can reach a very high top speed. Groups of electrons traveling through real wires and real light bulbs slow down considerably. This is what one electron could do if it was being slingshot. A bunch of them together get pretty slow. So, and that's not to say that all electricity is slow, but in a circuit where all the lights in the whole gym are connected in that circuit in a way that all of them will turn on eventually, but probably connected in parallel such that when one goes dead, then it'll all go dead. It takes us time, just a little bit for the whole circuit to warm up. It's also probable that it was designed to do that.
Designed to stay a long time or designed to be on the same?
Designed such that part of the room turns on first and part of the room turns on after. Or it might be built that way so that when it turns off, it goes in the reverse order. So that you next to the switch have the light longer. Like if the other end starts shutting off first. There's, the two answers I see are either it was built to do that, or the way the circuit is designed so that every light is in parallel with the others has the result of slowing it down.
Do you also happen to know why it makes that buzzing noise?
I said it, okay.
light bulbs have either a metal filament in them that is red hot and glowing, or have gas in them that becomes plasma and starts glowing. These are the types that have plasma in them. Most industrial lights are those. And the new CFL bulbs that are the spirally thing also have gas in them. Those light up because technically you're creating plasma or near plasma inside of them, which is gas that is so hot, it is vibrating so fast that it loses its own electrons and everything is shaking around free from each other. Which is to say it's very chaotic in there. So I guess I would assume that some light bulbs buzz because the plasma in them is too chaotic to not buzz. Since sound is just vibrations transferring into the air, if the gas is vibrating, it makes sense that those vibrations could then travel through the bulb into the surrounding air and then reach your ear. Last concept question for today. If an electron were pushed against the positive plate, just concept question, how much potential would it have? 0, correct. It doesn't want to go anywhere else.
That was chill.
That boy's chilling. Same as if you just had something sitting on the ground. But then it doesn't want to go anywhere else. It's where it wants to be. Potential is 0.
So when this thing, when all of the positive ones make it over to the negative plate and all of the negative ones make it over to the positive plate, is that when it's dead? Is that when it dies?
Well, if it's in a live circuit, more charges are constantly being introduced.
But if it's like the battery type?
Oh yes, in the battery type, once everything circulates through, it's dead.
What's the biggest capacitor?
You know those, if you ever passed by an electrical substation, like the fenced-in areas of all the poles sticking straight up and all the boxes jutting up out of the ground? I don't know for certain that those are capacitors, but they could be, the boxes. Yes,
How in the world does a solar panel work?
that's a good question. That is not part of this chapter, so this is not something you need to write down for test purposes. But solar panel works due to at least an application of the photoelectric effect. You know how you feel warmer when you're standing in sunlight?
Yeah.
So sunlight is energy. When sunlight hits you, you absorb that energy, usually as thermal energy. So it makes your particles start vibrating and get warmer. Well, if it strikes an electron, if the light hits an electron, it warms the electron up and makes it jump around and move somewhere. So the photoelectric basically says when light hits something, it can scramble and make electrons start moving. And solar panels are designed such that they are a good surface that when light hits it, electrons that are knocked loose by the photoelectric effect are funneled into a specific place in a specific direction such that they form electric current.
So could you not just put sunlight hitting one of these negative plates and it wouldn't do anything?
So,
If
say
you
that one more time.
had the sunlight hitting the negative plate of a capacitor, would it do anything?
That would probably be a good idea. That would be a very good idea. I assume that either exists, and if it doesn't, you should patent that.
Okay.
I would assume some technology like that would have been integrated, but that is a very clever thought, and I have not realized that before, so well done.
Yeah, that's our physicist up here.
I actually am not good at physics at all, so I'll let you.
You are allowed not to be.
I'll let you have it, get it, and it's not okay. And just run with it.
We will pick up with this next Thursday, since Tuesday is the 7th day, and everyone needs vacation.
And I ain't getting no vacation on there.
So the next set of homework is the Thursday with class or the one after?
The Tuesday after that. We're going to finish these notes next Thursday, and then we'll meet the Tuesday after that to wrap up the answering homework questions you have.
Okay, got it.
No class Tuesday, so next Thursday, they'll talk more about chapter 6. And then on the 23rd, we will wrap things up in the homework. You have a good day. Let me know if you have any questions about anything. And if I don't see you today or tomorrow, have a good weekend.
Bye, Grandpa.
Bye.
Take care.
You too.
Make good choices.
I'm planning on it. You too.